Hello everyone, and welcome to the very first video for this Outcompete channel. I created this channel to really focus on Python, machine learning, deep learning, basically everything under AI. Whether that's Sklearn or Scikit-Learn, Keras, TensorFlow, we're going to go through it all in many series to come on this channel. Now, as the first video, I'm going to be going over the Kaggle Titanic problem, and we're going to be using Sklearn to go over various algorithms that you can use, pre-processing methods, normalizing data, all that good stuff. Now, if you're new to programming, this is probably going to be a little bit difficult to understand, but in the coming series, I will be creating a full Python course from A to Z on YouTube for free. But I really wanted to just create something unique as the first video of the channel. So we're going to get right into it. Don't worry if you don't understand everything from the get-go. As I said, there's going to be coming series that will explain Sklearn, TensorFlow, Keras, everything in detail. And if there's anything that you want me to talk about in future videos, just leave it down in the comments. So first off, we can go to Kaggle, which is basically a site owned by Google where you can find data sets, challenges that you can compete for, where you can actually win money. So this is basically the holy grail of anyone that's going into AI. And I'm going to be attempting to do this live on this recorded video using Sklearn and other libraries. So I already have the data downloaded before starting the video, but essentially you would click join the competition and then you download the data, and then you can read up on the context of the data. So long story short, there's these features over here, survival, P class, a bastard class, or ticket class correction, age, number of siblings, number of parents, passenger fare, cabin number, and at the end of the day, you're trying to predict whether or not the passengers survived. 0 for no, 1 for yes. So this is a binary classification problem. Let's go ahead and use Google Colab. So Google Colab is pretty much like Jupyter Notebook. You can code everything directly into this notebook without downloading anything on your computer. No downloading libraries, nothing. Usually you do pip install TensorFlow or whatever in your command prompt, but with Colab, most of that stuff's already downloaded for you, and it gives you a nice virtual environment to work in. And you can even change the runtime input GPU just to speed up the training process in your machine learning or deep learning models. Now let's upload the data into this environment. Upload, and then we're going to upload just the train and the test. Now I'm going to import all the libraries we're going to be using. So import pandas as PD, which will allow us to manipulate data in nice, easy to access data frames. Import NumPy as NP. So this is basically creating arrays that you can do all sorts of things with for ML and neural networks. You can do element-wise multiplication and all that good stuff with different vectors and matrices. We're going to import matplotlib.pyplot as BLT, which is a visualization library, and Seaborn, which is built on top of matplotlib but has way better graphs, charts, and visualizations in general, so as SNS. Now we're going to import the data, the training data. So train data equals pd.read CSV train.csv. So we're just reading this whole CSV file into a pandas data frame. And if we want to take a look at the data, we just do .head, and we have the data over here. Now, when it comes to data, you're going to encounter a lot of data sets that might be missing values in certain columns, or might have features that are not even relevant. And you can even take features from already existing, or create features from existing features, and this is called feature engineering. So for example, you take the name column and you extract something unique from this column, for example, the Mr. and the Miss, and that's a form of feature engineering. You would drop this feature over here and create a new feature with just Mr. and Miss. So an important thing, you want to first explore the data before doing anything, get a feel of what's going on, and see how many missing values there are, all that good stuff. So we can start off by, first of all, using a count plot to see how many people survived on the ship. So what we do is SNS, which is Seaborn dot And for X, we can put the column name survived. And then we can put data equals train data. Now we get a nice visualization that shows us how many people survived and how many people passed away, unfortunately. So 0 means they did not survive and 1 means they survived. So we can already see that there's way more people that did not survive than survived. And we can go a step further and add a hue and put the P class, which is the ticket class, first class, second class, third class. And we can see that the majority of people that did not survive were in third class, followed by second class and first class. And the majority of people that did survive from the one column, which is one class, is the first class. This is important because now we have a feel of, what's going on. Next, we can see a histogram. So we could put sns.distplot, and then you can put train data, and we can pass, for example, age, just to see the age distribution. And we can see that in this data, the majority ages that were on the ship were from probably 20 years old to about 40 years old. Take this blue line out, you can put KDE equals false, just to get a histogram. Now, let's take a look at the data in general. So train data.info. This lets us know basically the data type for each feature. So we have ints here, and then floats, objects which are strings, categorical features, sex, like male, female, name, and such. Let's see how many missing values we have. So we can do train data dot is null dot sum. Now, based on this, we can see that there's 177 missing data points for age and 687 missing points for cabin. You can't just feed a model a data set with missing values. We're going to have to fill in these values and see which features we want to keep and drop based on their correlation with the overall survived or not survived. And also we're going to have to do some pre-processing because, as you see, there's some features that are strings. We're going to have to one-hot encode just so that it can be readable in a machine learning algorithm. So let's start off with age. Let's take a look at the age. Now we have 3 box plots, each one for each class, ticket class. So first class, we can see that the ages range from about 25 to 50. So it makes sense. The older people have more wealth. We can, create a naive hypothesis and say, older people have more wealth and thus they are in first class. And then you have second class, third class. And the average here is about 38, 39. In second class, it's about 30, and in third class, it's about 25. Now, since we're missing 177 values, we could just fill in these values with the average age of the entire data set, but that's not efficient. We want to actually be more precise. So we'll take the ages for each, the average age for each class, and fill them in for the missing values based on what class they belong to. So to get the exact numbers of the averages for each class, we can do. Okay, so in order to display the actual averages, we'll do train data, and we'll pass our condition here. So we'll do train data p class equals to 1, and then you can put age dot mean, and we get 38. And then do the same thing for the other classes, so 2, 3. And actually, to visualize it, you put print. And we get 38 as average age in the first class, 29 average age in the second class, and 25 in the third class. So now we need to figure out a way to actually go in to the data frame and replace all the null values in age with these values. So we're going to have to create, first of all, a function that does that, and then we'll apply it to the data frame. This is how we're going to do it. So put def, and then we'll say fill in NA values, and we're going to take columns as a parameter. And then we're going to say age is equal to column 0, and p class is equal to columns 1. So the 0th index and the first index. And then we're going to say if pd dot is null, age, and then another statement to check which class they're in. So if p class is equal to 1, return x. We're going to fill that out in a second. Then elif p class is equal to 2, return x. Elif p class is equal to 3, return x. And then else, return age. Now we're just going to copy paste what we did here and put round so it can seal the value, because there's no such thing as, or we'd rather have a whole number. If it's 38.2, we'd rather have 38 as the inputted age. So get the second value here, round, and the third value. Okay, so we created the function, and now we actually have to apply it to the data frame. And just to go over what this is doing exactly, we're going to feed it in a data frame with 2 series in it. It's going to have age and p class, and it's going to take the values of age and p class based on the 0 index and the first index, and it's going to ask, well, is pd null? And it's going to test age, and if they're from the first class, then we're going to assign this value. If it's second class, we're going to assign this value, and third class, we're going to assign this value. Otherwise, return age if it's not null. Now we do train data age equals train data age dot apply, and then fill in NA values. We're going to pass age and p class. Let's see, p class. Yep. Let's see what that does. Okay, so now if we refresh the data frame, oops, is null dot sum. Okay, so we did something wrong here. Let me see. Okay, so I found the error. I was missing the axis equals 1 as the second argument in apply. So essentially, when you run train data is null.sum, we can see that the age is no, or the values in age, the 177 missing values are no longer missing. We just fill them up with this function we created here. Now, going forward, we have the cabin class. So let's take a look at the cabin class. We can create a heat map of the remaining null values. So train data.is null, and you can just quickly visualize. And there's a lot of values in cabin that are missing. And if we look at the data of cabin, where is it? Right here. Or actually, whoops, head. It just says, you know, C85, C123. Since there's a lot of missing values, we're just going to drop it. So what we can do is train data dot drop, and then we can pass in cabin, and then axis equals 1, and in place equals true. Now, if we look at train data dot head, we can see that feature has been dropped. And then I believe there's still 2 more missing values right here, embarked. So the way we can deal with this is put train data dot is null, or dot drop NA in place equals true. Now if we look at train data dot is null dot sum, we can see that we have no more missing values. Now the next step is to look at each feature and see which ones we want to keep and which features we want to drop. There might be some features that are not as important, such as ticket, fare, yeah, so for name, we're not really going to be able to do that much. You could feature engineer, but we're just going to drop it for this situation. Sex, we're going to keep. We can drop passenger ID, and because essentially it's the same thing as the automatic index of pandas. But you will need it later on when you're actually creating your predictions in the test data in order to submit it to Kaggle. And we'll drop ticket. We'll keep everything else. So we'll hot encode embarked and sex. So what we're going to do is train data.drop, pass it in a list of the columns that we want to drop, and we'll put passenger ID. We're also going to drop name. We're going to drop ticket and axis equals 1. In place equals true, and this argument here, in place equals true, basically just makes the change happen automatically to train data instead of having to actually put train data equals. So let's run this and then look at the head again of the data. Good. Now the next step is to actually one-hot encode the categorical columns, so sex and embarked. What one-hot encode does is essentially it'll change these categorical values into 0 or 1. And if you want to say how many unique values there are, you can do train data sex dot unique, and you get all the unique values. Same thing with embarked. So copy paste here. We see that there's 3 separate values, or 3 unique values in embarked. So we can one-hot encode it. Alright, so we're going to use pandas to one-hot encode these categories. So what we'll do is train data sex, or actually sex equals train data sex pd.get dummies axis equals 1, or my bad, drop first equals true. And then if you look at this series, we can see that male and female became 0 and 1. Now we're going to do the same thing for embarked. So just copy paste embarked, and then take a look at the embarked data series, and we can see that we have QS. And the reason we did drop first is because, if it's not Q, it's not S, then it's going to be the third option. If it's 0, 0, then the third option, which is C, I believe, is the case. And for male and female, instead of having male, female, 0, 1, we just need one column. So if you look, we just need one column here, because if it's one's male, for example, then 0 would be female. We don't need 2 columns. Okay, so now we actually have to drop sex and embarked from this data frame and add these, or concatenate them into the data frame. So the way we do this is train data dot drop, and then pass it a list sex embarked axis equals 1, in place equals true, and then we're going to do train data equals pd.concat train data past the data frame, and then the data series that we just one-hot encoded. So sex and embarked axis equals 1. Run that. Now train data.head. Okay, so we successfully one-hot encoded the sex and the embarked columns. We dropped them and put the new features that we just encoded, and we pretty much did a lot of the pre-processing. Now the next step would be to actually scale or normalize the data. And normalizing essentially makes all these values between 0 or 1 depending on the scale used, and it just makes all these numbers very small numbers that will make the machine learning algorithm or neural network perform more efficiently and read the data better, instead of having different values in each column. So what we can do is from sklearn dot preprocessing import, we'll use the min max scaler. Then what you do is you have to instantiate the min max scaler, so we'll put scaler equals min max scaler, and then scaler dot fit transform. I skipped a step here, so we're actually gonna split our data into test sets and training sets, and then we'll scale, because you don't want to fit transform on your entire data set, or else you'll have leakage on your test set. We want to only fit it to the training set and then transform on the test set. So from sklearn dot model selection import train test split. So this will allow us to easily take our training data and split it into labels for training and testing. So we can do x train, x test, y train, y test equals train test split. Here we're going to pass our data frame. Okay, I also skipped a step. It's been a long day, guys. So we're going to create x equals and y equals. Here we're going to put data train data dot drop, and we're going to drop the survived column. And the reason we're going to drop the survived column is this is going to be our training set, and the training set should not have any labels. And then here we'll give it the labels, the y variable. So we'll do train data and then survived, right? Run that, whoops. And then we're going to pass here x, y, and then test size, which essentially is a argument that you can set in order to give it the percentage you want of the data to go towards the test data. So we're just going to use a 0.1 or 10%. So we'll have 90% training data and 10% test data or validation data. So we did that. Let's put that in another line. We ran it. It worked. Now put that back here. Scaler equals min-max scaler. So this is instantiation of the min-max scaler, and then scaler dot fit transform. And we're going to put our x train, and then we're going to say x train equals scaler dot fit transform. Now fit transform is a easy way to do the following. Normally you would just do x train equals scaler dot fit x train, and then you would do x, or correction, and then you do x train equals scaler dot transform, and then x train. But there's an easy way to just call this line over here, and then we can do x test equals scaler dot transform x test. So remember this data frame over here, we have 22, 1, 7.2. Now you're going to see the new scaled data frame. So if we do x train dot head, or correction, just x train, you're going to see that the values have been scaled. Now we're ready to put it into some kind of model. So we created our train test split. So we have our x train and our x test, y train, y test. Now we're going to use various models from sklearn in order to approach this problem. So the first one we're going to use is the support vector machine model, so SVM. So we do from sklearn dot svm import svc. There we go. And then we're going to instantiate svc. So we'll say svm equals svc, and then we're going to fit our data into this model, the SVM model. We're going to pass x train and y train. Now we're going to do predictions equals svm dot predict x test. And if we run this, oops, it worked. Now, in order to see the accuracy, we do from Scikit-Learn dot reports or metrics import classification report and the confusion matrix. Then we'll say print, just copy paste, classification report, and it takes the parameter the y test, so the true labels, versus the predictions of the model, and then do the same thing for the confusion matrix. So here we have our classification report and our confusion matrix. The precision, recall, F1 score, and support are metric values that you can use along with accuracy. We got a 79% accuracy here, 77% on the precision, 95% on recall, 85% on F1 score. Now, accuracy essentially is the number of correct predictions over the total predictions. Recall is the number of true positives over the total number of true positive and false negatives. So, depending on the situation, depending on the context of the data, you'll have to look at each metric differently. So for recall, essentially tells us or identifies all relevant cases in a dataset, and the precision identifies only relevant data points, and the formula for that is number of true positives over number of true positives plus number of false positives. And then the F1 score basically combines recall and precision, and it's precision times recall over precision plus recall. We call this the harmonic mean. So this got 79%. Now we're going to try to better perform this model, and we can do something called a grid search with support vector machine models. So what we do is from Scikit-Learn model selection import grid search as CV, and then we're going to instantiate it. We're going to say grid equals grid search CV, and it's going to take the parameter SVC, and then param grid, which we're going to create, and in place equals true, and here param grid is equal to, and then we're going to create a dictionary C, and I'm going to explain this in a second, C and gamma. So essentially, for this intro video, all you need to know is C and gamma are two hyperparameters that you can tune using grid search to better perform your model. And you can read up on C and gamma. I'll explain it in further videos, but essentially, we're just going to give an arbitrary amount of numbers in this list, and then it's going to go through every single value in the list and see which parameter is the best one that gives the best metrics. So 0.5, 1, say 10, 50, 100, and 1,000. So we have 1, 2, 3, 4, 5, 6 values here. And then gamma, we do 1, 0.1, 0.001, 0.0001, 1, 2, 3, 4. There we go. Okay, so we created a param grid. Grid equals grid search CV, SVC, param grid, and then not in place. Refit, there we go, equals true. I think that's it. And then we do grid.fit, xtrain, ytrain, grid predictions equals grid.predict, xtest. Let's run that and see if we get an error. And we did not get an error. But I forgot one more parameter. To see what's going on, we can put verbose equals 2. And it's going through all the parameters we put in the lists for the gamma and the C. And it picks the best one. And then what refit does is it ensures that it uses those variables for when we're actually fitting the model to the data and predicting. Now to see the predictions, we can just copy paste this code here and replace it with the grid predictions. Run that, and we can see we scored a higher score. So we got 81% as accuracy here compared to 79, so we increased our accuracy by 2%. Our precision got 79% for the 0 class, 86% for the first class, and then 95% versus 58%. So you can see it beats this model. 86% here, 69% here. So this was using SVM. Not bad, but obviously through feature engineering we can really get better scores for these metrics. So feel free to go back to the data, do some feature engineering, maybe leave some features out or leave some features in, or create your own features, and see how they actually increases. Now we're gonna use another model. We can use logistic regression, so we can say from Scikit-Learn dot linear model import logistic regression, and in another video I'll explain what each individual model does. I'm just basically trying to show you the code for all of these models and then create in-depth videos explaining each algorithm and what it does in the background. So here we're gonna say LR for logistic regression equals logistic regression. So we instantiate it, and then LR.fit xtrain ytrain LR predictions equals LR.predict, and we're going to do the X test, and then we'll actually print it out. So here we got an accuracy of 79%. So the SVM with the grid search performed better. So far it's at 81%, beating the logistic regression algorithm. Now, I forgot to talk about the confusion matrix, but if you just type in confusion matrix, essentially it's a grid, and this represents positive and negative. So true positive is the number of true positives in the model that I predicted correctly, and then the number of false positives. So I believe this is a type 1 error. And then you have false negatives, which is a type 2 error, and then your true negatives. And that's what this confusion matrix represents. Okay, so now we're gonna use the k nearest neighbors and see how that performs. So we'll do from Scikit-Learn dot k or neighbors import k nearest neighbors classifier, and then we'll just instantiate k nearest neighbors classifier into knn, and then knn.fit fit our data into the model, x train, x test, and then knn predictions equals knn.predict, and we're going to pass the X test. And then same thing, we're going to see how the model performs. Oops. Run it. Oh, whoops. X train, Y test. What? X train, Y train. Okay, so this model got an accuracy of 85%, beating the SVM, or support vector machine model, and the logistic regression model. So this model performed pretty good, but we can tune the k nearest neighbors in order to try to get a higher accuracy. So what we can do, just to show you, is you can actually set the amount of k. You can set k as n underscore neighbors, and essentially in k nearest neighbors you have different data points, and the closest data points get selected. So if you put 3, then the closest 3 data points to your data point will probably be selected. And I know it doesn't make sense that much. I'm going to create a future video that explains this in depth, but I just want to show you the difference if we set the nearest neighbors to 1 and then we keep changing the number, and how we can automate this process for it to automatically pick the best one. So if we put 1, our accuracy drops to 74. If we put 2, it goes to 83%, it goes 3, it goes to 87%, and if we do 4, it goes back to 83% in terms of accuracy. So what we can do to get an automated process of picking the best n neighbors argument is the following. We can do for I in range 1 to 40, copy paste this model, and for nearest neighbors we're going to set that to I. And essentially what this is going to do, it's going to go from 1 to 40 and try every single number from 1 to 40. And we're going to create a list here. So error list. And we want to find the lowest mean absolute error in this model. So what we could do is error list equals or dot append. And then remember we imported numpy, so np.mean. And we're going to say KNN predictions is not equal to y test. So take the average of all the values where KNN predictions is not equal to the true label, essentially where it's wrong. And if we let this run and look at error list, we can see the mean absolute error in this list, right? The average in each iteration. So essentially what we can do here is we pick the one with the least error, and just to quickly visualize it for you, we can actually pass this into a data frame and then visualize it. So what we'll do is say error list df equals pd dot data frame, or actually no, plt dot plot and range 1 to 40, because that's what we did. And you can say this is the iteration, and then for the y value we'll pass the actual error list. There we go. So we can see that as it's training different n neighbors, the error goes all the way down at like 3, and then it starts to go up. So we want to stop it right here. We want the n value at this point, and what we can do to see the absolute lowest error and the index that it's at, we can say np.arg min and then pass error list, and it'll actually give us the value 2. So the second index, or correction, third index, because it starts at 0, 1, 2, we can use this for our n value. So where is it? We take this model here. Oh, and just to prove to you that that's the lowest value, we can say error list 2, and we get 0.13. And if we look at the whole list, we can see that 0.13 was actually the lowest value. So we're going to set actually n to 3 because we started at 1, right? So 0, 1, 2. Told us index 2 is the lowest value. So this will be k equals 3. So we go back, put our model, put 3, and let's see how this model performs. And then get this. There we go, 87%. So that was just an automated way of finding the best k value for the k nearest neighbors classifier. So far, out of all the models, the k nearest neighbor seemed to perform the best. we have 87% here. Now, we could try decision trees and random forests. So for this, we do from Scikit-Learn dot tree import decision tree classifier, and then we're also going to import the random forest. So Scikit-Learn dot ensemble import random forest classifier. Now let's instantiate both of them and run them both at the same time just to save some time. So we'll say decision trees dt equals that, and random forest classifier equals that, dt.fit x train, y train, and then RFC, and then decision tree predictions equals dt.predict x test, and then change this to random forest classifier RFC dot predict, and then we can print them individually. So run this first, and then let's see. We'll run the decision tree first, and then we'll run the random forest classifier, and I'll show you how to actually tune the random forest classifier to increase the accuracy. So this is the decision tree. You got 79%, and then the random forest classifier, it's running. Whoops. It got 76%. Now what we can do to increase this performance is actually add a argument here. Where is it? And this is n estimators, so the number of random trees you want in the model, and we'll put 200, and actually went to 75%. So in this situation, which is weird, the decision tree beat the random forest classifier. So if we change this to 100, let's see how this affects the values. So now it went up to 76%, change it to 25, it went to 81%. So when you put the number of trees to be 25, now it beat the individual decision tree with the 81% accuracy score. So I just showed you different models. Decision trees, random forests, we did the k nearest neighbors, we did the logistic regression model, we used a grid search for the support vector machine model, and from every model that we used, it appears that the k nearest neighbors performed the best. We got an 87% accuracy. Now, obviously, you can play with these numbers and try to increase your accuracy in other metrics by feature engineering. So going back to, the data frame here and seeing which features you should keep, which ones you should drop. Maybe keep the name, but take out just the Mr. and the Miss. Or find the names, the most common names that belong to first class, second class, third class. So many things that you can do with feature engineering, and we're going to cover that in different series to come. But yeah, the final step, which you can do essentially, is do everything we did, but with the test data, and then you can actually submit it to Kaggle and see what your accuracy is, and you'll see you're actually here in the leadership board. So the highest score obviously is 100%. Our model did 87% on our test data with the k nearest neighbors. So there's a lot of work to be done to improve the model. And I just wanted to point out, when I'm referring to test set, in real terms, it's a validation set, because you should have a train set, you should have a validation set, and then a test set. We were using test set in this case as the validation set, but down the road, we'll show you videos on how to split the data into three: a test set, validation set, and a actual test set. So thank you for watching the very first video. I really hope you enjoyed it. And if there's anything specifically that you want me to talk about in future videos, leave it down in the comments.